This is the continuation of review of exam 3 in preparation for the final. And here the next question would be question 10. In the Zoom meeting, we went, I think, all the way to 31. All right. So this is the next in line. Here we are. The question is how these factors, the Ka for an acid, the concentration of the acid, affect the percent ionization of a weak acid in water. Now, when we are asking about the percent ionization, all right? So in other words, what you are looking at is how much acid is ionized. Okay, so that's what the percent ionization tells you. A larger percentage tells you that there are more of the acid ionized, and if you have more of the acid ionized, then the acid is stronger. Okay, so that's the connection between percent ionization and strength of the acid. And a stronger acid will be more ionized, and that corresponds with a large Ka value. Therefore, if you have a large Ka, then the percent ionization, the percent ionization will increase. Okay. Now, the next one is not so evident, because with a low concentration of acid, well, will it increase, will it decrease, or will not change the percent ionization? And truth is, a low acid concentration also have a larger percent ionization. Okay. Now, what is the meaning of this? Why is it a low concentration of acid have a larger ionization? Think in terms of the room that the acid has to ionize. Okay, so remember, a weak acid doesn't really want to ionize, so it's just a small fraction of the acid that is ionized. So if you increase the concentration of the acid, then the acid is less likely to ionize. Why is that? Well, think in terms of how much of the acid is already present in the solution, right? So the ions that you're producing want to recombine back to the acid. So the more you have out there, the more ions you have, then the more likely they are to recombine, because there is not much space, right? In the solution, that is. Okay, so the low acid concentration, there is more freedom for these acid molecules to separate. Okay, and that's why the percent ionization increases. So one of the examples that I've been using with people that has asked me about this question before is imagining a ballroom in which you only have a few people dancing, and they have more room to move freely around the ballroom. Okay, so but if you increase the number of people dancing, then they don't have so much room and they are closer together. So that's kind of what you are looking at here. If you increase the concentration of the acid, then those molecules will be closer together, and then there is not much room for them to ionize. Okay, so that's why a low acid concentration will increase the percent ionization. A higher acid concentration will decrease the percent ionization. Now, here in this question 27, we are adding 2 milliliters of 0.25 molar sodium hydroxide to a buffer that contains 0.80 molar of acetic acid. And since we are naming this acetic acid, then all we care about this is that it's HA and 0.20 molar of A minus. That's all we care about here. So we are adding 2 milliliters, 0.25 molar sodium hydroxide to 10 milliliters of something that contains 0.80 molar HA, 0.20 molar A minus. Okay, so the typical way to go here is to calculate number of moles of each. So in this case, remember, if we change these milliliters to liters, then it's 2 10 to the negative 3 liters. And same goes here with the 10, so this is 10 to the negative 3 liters. All right? So if you multiply this, 2 10 to the negative 3 by 0.25, you obtain 5 10 to the negative 4 moles sodium hydroxide. If you do the same for HA, you obtain 8 10 to the negative 3 moles HA. And if you do the same for A minus, you obtain 2 10 to the negative 3 moles of A minus. Now you have sodium hydroxide, all right? Who is sodium hydroxide going after in your buffer? Well, sodium hydroxide will react with HA. And the reaction is 1-to-1, right? So 1 mole of HA will react with 1 mole of sodium hydroxide. Therefore, the change for sodium hydroxide would be minus 5.10 10 to the negative 4. HA will be 8 10 to the negative 3 minus 5 10 to the negative 4, so the number of moles of base that you added, of the sodium hydroxide that you added, and A minus will be 2 10 to the negative 3 plus 5 10 to the negative 4. Okay, so why did you subtract 5 10 to the negative 4 from HA? Because HA is reacting with the base, the sodium hydroxide. Why are you adding 5 10 to the negative 4 to A minus? Because A minus is being produced through that reaction. So in case you wanna just verify that that's the case, then sodium hydroxide plus HA goes to A minus plus water plus sodium, which we don't really care about those two. All right, so the main protagonists here are HA and A minus. So the changes are going to be negative for HA, positive for A minus. Okay, so that if you want to calculate the pH now, pH will be equal 474, that's the pKa, plus the logarithm of the base. Okay, here you will obtain 7.5 10 to the negative 3, and this is 2.5 10 to the negative 3. Therefore, here you have 2.5 10 to the negative 3 and 7.5 10 to the negative 3. All right? Remember, it's the base over the acid. And here, you're supposed to obtain 426 as the answer. Okay? Now, this question, all right? You have to calculate the pH of a mixture of acids. Okay? This is a mixture of acids. So who's controlling the pH? Well, technically the one controlling the pH will be the stronger acids. If they are equally strong, then you have to account for contribution from both. But in this case, if you have a weak acid and strong acid, which is the case, then your strong acid is the one controlling the pH. All right? And if that's the case, well, guess what? You can completely forget everything about your weak acid, and the strong acid is in control. So that's the only thing that you have to consider. Therefore, your pH here is just minus log of 0.10, and this is equal to 2.0. Okay? So once again, the strong acid controls pH in presence of a weak acid. Okay, so this is negligible contribution. Okay, so your pH is 2.0. All right, which statement describes how absolute concentrations of a weak acid and its conjugate base affect the capacity of a buffer solution? All right, before we do anything, buffer capacity. All right, what's important to know here? High capacity means high concentration. Ideally, both. Okay, ideally. Okay, why ideally both? Because if you have high concentrations of both, you can resist changes in pH in both directions. If you are acid or if you are base, you may have a high concentration of just one of the counterparts, but that will give you resistance to pH change in only one direction. So if you have a high concentration of your acid, all right, and buffer, then you may resist addition of base to that buffer, but it might not handle addition of base. All right, so that's why the high capacity is associated with high concentration of both. Okay, that will give you a high capacity buffer. Okay, so here, what's high, what's low? Well, when you look at the numbers here, you have 0.45, all right, and somewhere you have 0.045. That's 10 times lower, all right, which means in this particular problem, high is 0.45 molar, low is 0.045. Okay, it's basically you have two concentrations, whichever is higher, that's your high capacity buffer, whichever is lower, that's your low capacity buffer. Okay? Now, you have relatively high concentrations here, that will give you a high capacity buffer. Okay? And the explanation for that is because a small increment of added acid or base is effectively neutralized. Well, that's exactly what you want, right? You want a buffer. The purpose of the buffer is to neutralize acid or base added to that buffer. And if the buffer is high capacity, then you have high concentrations of both. Okay? Now, the next one, well, we already know that these are low concentrations, and low concentrations will not give you a high capacity buffer. Okay, so that's why this one is not a description for what a buffer does. All right. Now we have here 0.45 molar and 0.45 molar. We have determined that that represents high concentration. Therefore, will give you a high buffer, not a low buffer, a low capacity buffer. Okay. So those concentrations, and you have the conjugate acid base pair. Okay, and it's a weak acid base pair. So this will be a high capacity buffer actually. So that's why we don't pick this one, because it's telling you that those concentrations is associated with a low capacity buffer. Okay? Shoot. So here we have, okay, the first one is not what you're looking for. Okay, here you have a conjugate acid base pair. A weak acid conjugate acid base pair. Okay, and you have high concentrations, and that will give you a high capacity buffer because the small increments of added acid or base will be neutralized. Okay, so this is the correct one. Why is this one not the case? Because you have a weak acid. Let's change the color here. You have a weak acid with a strong base, okay, and you have equal concentrations of both, so they will completely react, and then you only have, let's highlight this entire thing. In this case, you only have the conjugate base present. Okay? And so you don't have a buffer. You don't have a buffer because you don't have significant concentrations of both. All right? So because you only have the base present, this is not a buffer, actually. Now, in this case, which indicator would be most appropriate to signal the equivalence point on a titration of 1 molar sodium cyanide with HCl? Okay? So if you are titrating with HCl, which is a strong acid, well, this is cyanide, right? Cn minus. Okay? This is a weak base. What happens on equivalence? So the reaction is actually Cn minus plus HCl going to HCN plus Cl minus. We already know that this is inactive. It has nothing to do with pH. But this is a weak acid, and as such will give you an acidic pH. Okay? So at the equivalence point of this titration, you are expecting an acidic pH. Well, we look at our options here, right? So first is Kresoff-Stalin. And crystalline is this one, which is a basic pH. All right. Then we look at phenol red, and phenol red is this one. So you are, well, at pH 7 it should be yellow, so the change in color starts above pH 7, so it's also basic, slightly basic indicator. Then I'm gonna skip brown crystal green, I'm gonna jump to alizarin yellow. Alizarin yellow is here. So all these three are basic indicators. Indicators that will change color in basic pH. What are you looking for? You are looking for an acidic pH. Your only other option, let's scratch this. Your other only option is the brown crystal green, which is right here. Okay? You don't have to worry about this one. You don't have to worry about this one because you are not given the option of selecting those two. So out of the four indicators that you were given, only one is acidic. Therefore, only one is suitable to use in this titration. Okay, what is the pH of a 0.0085 molar calcium hydroxide? Okay, so this is calcium hydroxide. All right, in water it will dissociate into calcium 2 plus and 2 hydroxides. All right, so if the solubility of this, if the concentration of calcium hydroxide is 0.0085, well, it means that calcium ions will be equal to 0.0085, but the hydroxide is going to be 2 times 0.0085. So obviously, the most common mistake in this question was that people forgot about that 2. All right, so your pH will be equal to minus log of 2 times 0.0085. Now the pH, the pOH, is equal to that. All right, so it's logarithm of 2 times 0.0085. That's equal 177. Therefore, your pH is 14 minus 177, and that's equal to 1223. Okay, 2 decimal places. So remember that you have to add those 2 decimals there. Not significant figures. If you are to provide a pH, most likely is with 2 decimals. Okay, here we want to prepare a buffer with a pH around 262. Okay, and we want to select the 2 components that will have similar concentrations, and that we're gonna give you a pH of 262. All right. So first things first, if we convert this to pKa, we are going to get 2.5 negative 3. This is 260, and this is 9.3 negative 9. So this is 803, but this particularly, this is pKb. Okay, because you are working with Kb. All right. So here the pKa will be equal 14 minus this, and that would be 597. All right, because when you're looking at buffers, you want to see from the point of view of the acid. So the pKa of the conjugate acid in that buffer will give you the working pH for that buffer. All right, so that means that fluoroacetic acid would be good to prepare a buffer around 260. That's exactly what you're looking for. All right, so your buffer is supposed to contain the fluoroacetic acid pair. All right, the fluoroacetic acid plus the conjugate base. That means that pretty much we can discard this because you don't have fluoroacetic acid there. you can discard this one, okay, because you have the acid but you don't have the conjugate base. That's not going to give you what you need, okay. Here you have the acid but you are adding more acid, so that doesn't help you produce the solution that you need, okay. And this one would be the correct because you have the acid, you have HA, and you have A minus, okay. So that's what you need to prepare this buffer, okay. You have equal concentrations of those two, all right. The two components are at similar concentrations, all right. A pKa of 260, if they are equal concentrations, well, you are almost right on the spot, okay. Which two factors increase the Bronsted acidity of an oxoacid of a main group element? No partial credit will be given, okay. So the oxoacids, so you have HO, and this is connected to another central atom, all right. How do you increase the acidity of this acid? Well, number one, if you increase the number of oxygens, okay, large number of oxygens, okay, that will help increase the acidity. So this is one. You need a large number of oxygen atoms, not a small number, and you want X, this central atom right here, you want them to be more electronegative, because if it's more electronegative, it's pulling more electron density from oxygen, and if you pull more electron density from oxygen, then oxygen becomes less able to keep the proton, okay. Therefore you are weakening the hydrogen oxygen bond, and therefore you make the acid stronger, okay. So you want a high electronegativity of the central atom. Okay, consider the salts. We have C5H5NHCl, Na3PO4, and KBr. And we want to know which one of these salts will give you a neutral, basic, or acidic. Therefore, the learning concept here is acid-base behavior of salts, so that doesn't have to do anything with saturation, actually. All right? So remember, neutral, a salt will be neutral if both components, or both ions from that salt, come from a strong acid, strong base. So KBr, K plus, Br minus, this is coming from HBr, this is coming from KOH, both strong acid and bases, so this is going to be neutral, okay? Sodium has a similar origin, so it's coming from sodium hydroxide, but PO4 is coming from HPO4, okay? And as such, well, it's an acid, doesn't look like the list of acids that we have, so this is a weak acid. Therefore, this PO4 is going to be a weak base, and therefore this one will be basic, okay? Now this is pyridinium chloride, okay? So if it's chloride, remember chloride is Cl minus, so we can take this out because this is coming from HCl, strong acid, so Cl minus doesn't have anything to do with it. If that's Cl minus, then this is C5H5NH plus. And as such, remember the cations usually come from a base, so this is a weak acid, and as such will behave as an acid. All right? So a 0.075 molar solution of a known acid is 0.0872% ionized, okay? What is Ka? So the percent ionization, and let's change the color here. The percent ionization, pretty much the shortcut to percent ionization is that X divided by HA times 100 give you the percent ionization. Okay, and this is 0.0872. Okay, and what does X mean represent here? X is the concentration of H3O plus. Since you only have acid, or you started with acid from the beginning, then X is also A minus. Okay, so we have the concentration of the acid, so this 0.075 here is HA, therefore X will be equal to your percent ionization times HA divided by 100. So this is equal to 0.0827 times 0.075 divided by 100. All right, and this is 0.0827 times 0.0872 times 0.075 divided by 100. So X here is equal to 654 10 to the negative 5. All right, for any given acid, when HA goes to H plus A minus, then Ka will be equal to X squared divided by HA, and this will be equal to 654 10 to the negative 5 squared divided by 0.075. All right, so this is squared divided by 0.075, and Ka is equal to 5.7 10 to the negative 8. Select the role of each species in this Lewis acid-base reaction. All right, so an acid, okay, remember we are working with the Lewis acid-base theory. An acid is electron deficient. A base is electron rich. Okay, so when in doubt, if you have a positive particle, most likely that's going to be a Lewis acid. If you have a negative particle, then that's going to be a base. Therefore, your fluoride is the Lewis base, your iron is your Lewis acid, and then you only have one compound in the product side. Well, that is your adduct. Okay. The concept of buffer in the Lewis acid-base theory is a little blurry because it's more a reaction thing that is going on here. It's not necessarily an equilibrium, although can be represented as an equilibrium, but that's not exactly something that you need to worry about. Okay, this probably is one of the most straightforward questions that we have in the exam. This is simply a buffer question. All right, so you have the concentration of both components in the buffer. You have the pKa. So if you have the acid in the conjugate base, then pH is equal to pKa plus the logarithm of base over acid. Okay, so I did say this was the most straightforward. That doesn't mean that you cannot make mistakes here, particularly if you switch these two, which is it's actually rather common to happen. All right, but here we have the pKa, correct? So pH equals pKa 489. All right, here you have to identify that this H, I mean, we are telling you this is propanoic acid, right? So this is HA. And then you have the propanoate here. The only thing that you need really care about this is that, well, sodium doesn't count. And this actually looks like the acid without the proton. So this is your base. All right? So the concentration of the base is equal to 0.54. And the concentration of your acid is 0.22. All right? So your pH here is 489 plus the logarithm of 0.54 divided by 0.22. and this is equal 528. What is the pH of a aqueous solution of HN3? Okay, that's another thing that we're saying, right? So HN3, you are being given Ka. There, we are not giving you anything related to the structure of this. So the only thing that you can assume is that this is an acid, right? So, and as such, well, is HN3, and there were another question in which this particular acid appears. So, you know, there were kind of, what's the name of that, Easter eggs in the exam that you can use to your advantage. Not to expect that every single time, but in that case it helps. So this is an acid, you have the constant, you have a concentration that is 10 to the negative 1. We're comparing that to the 10 to the negative 5, so the approximation that x small is valid. Okay, we can assume that x is small, and if that's the case, Ka is x squared divided by HA, and therefore x will be the square root of HA times Ka. All right, and since we are using Ka here, x represents H plus. All right, so x will be equal concentration of acid 0.25 times 1.9 10 to the negative 5. This is equal to square root of 0.25 times 1.9 negative 5. This is 0.00218. Therefore, your pH is minus log of that number. And that would be equal to 266. Okay, which equation describes the ionization of water? Well, ionization of water is two water molecules will ionize into H3O plus OH minus. Okay, this is a pure liquid, therefore Kw will be equal to H3O plus times OH minus, and therefore that is the correct answer. In this one, we want to know what expression you would use to calculate the pH of the solution. All right? Sorry, yes, to calculate what we're calculating Ka for the weak acid. All right? So remember, this is HA going to H plus A minus. Therefore, Ka is H plus times A minus divided by HA. But since everything is coming from the acid, then H plus is equal to A minus. Therefore, we can use this. Ka equals H plus squared divided by HA. All right? And if you have the pH, then H plus is equal 10 to the negative pH. So basically, we can take this, substitute it there, and then we end up with Ka being equal to 10 to the negative pH squared divided by HA. Okay? Which is pretty much this expression that we have here. What type of titration does this curve show? Well, you are not starting, number one is low pH, but not so low, okay? And more important, there is a small jump there, okay? Therefore, the small jump is telling you that is weak. The low pH is telling you that's a distant acid, okay? And of course, if you're starting with an acid and here you are at high pH, Typically what you use to titrate here is a strong base. Okay, so this is a weak acid strong base titration. Okay, weak acid strong base. How are Ka and Kb of a conjugate acid-base pair related to the Kw of water? Well, we can cut to the chase here, right? So it's the same relationship that you have with the H plus and the H minus. So this is similar to Kw being equal to H plus times OH minus. All right, and the other one that you need to know is that if you take minus logarithm of in both sides, then you get 14 equal pH plus POH, and the similar to this is that 14 is equal to pKa plus pKb. All right, remember this always goes for a conjugate pair. Okay, so those are the numbers that you're using there. Okay, Ka values for this acid. We can assume that this is a triprotic acid because you see 3 protons there. Okay. Each value with the description, well, Ka1 is larger than Ka2 and larger than Ka3. All right. So if we identify which one is larger, okay, this is the largest one, so this is going to be Ka1. This is the medium, so this is going to be Ka2, and this is the smallest, so that's going to be Ka3. There is no Ka4 here. Here rank the strengths of each acid. Okay. Stronger acid means larger Ka. Okay. So the larger Ka is this one. Therefore, can't remember what the options there were here, but this will be the strongest. This one over here is the smallest Ka, therefore HNO3 will be the weakest, and this will be the intermediate. All right. And here, by far the easiest one. What is the pH of an aqueous solution with pOH equal to 435? If 14 is equal to pH plus pOH, then pH is equal to 14 minus 435. And this was 965. Okay, can't remember this. This was above 90% performance. All right, so that's it for exam 3.